Alright, we're about to do a second example where we're going to find out the orders of a number of reactants in a complicated reaction. So we're looking at the following redox reaction between permanganate and chlorate in acidic media. And what you can see here is a table that gives the concentration of permanganate chlorate H+ along with the initial rate of this reaction. So what we have to do is find out the orders of each one of these reactants, and the generic rate law for this reaction is -K times the concentration of permanganate to the power of X. We don't know what that is. We're going to find out in a little bit. Times the concentration of chlorate to the power of Y times the concentration of H+ to the power of Z. Alright, so we try to locate any two rows for which any of the reactants has a value that is constant. And luckily for us, if we look carefully, we'll notice that the first row and the second row happen to have the same concentrations for chlorate as well as the protons. So we could use rows 1 and 2 to basically cancel out chlorate and H+ from the equations. So we're going to do just that. We're going to divide the rate of the first row by the rate of the second row, in which case the rate constants cancel out. You can factor out the power of X outside of permanganate. You can factor out the power of Y outside of chlorate and the power of Z outside of the protons to, basically have the equation look in the following format. But as stated before, when you plug in the numbers, the following happens, right? The values of chlorate for runs 1 and 2 and the value of the protons for runs 1 and 2 are the same, so they cancel out. And the only thing you have left behind are the fractions of the rates along with the fraction of the permanganate concentrations. So if you look at that value, right, and carry out the calculation in your calculator, 5.2 times 10 to the negative 3 divided by 3.3 times 10 to the negative 2 equals 0.157. 0.1 divided by 0.25 is 0.4 raised to the power of X. And here you probably want to take the logarithm of both sides in order to bring the exponential value of X to the front of the log, right? And so to solve for X, you will have to divide the log of 0.157 by the log of 0.4. And plugging that in your calculator should tell you that the value of X is actually 2, meaning that the order of permanganate is second order. Okay, so we found out the value of permanganate. So now we're going to try to go after one of the other two. So let's look at the table really carefully. So there's a number of things we could do. We could select rows 2 and 3 for which the concentration of H+ is constant, or we could select rows 2 and 4 for which the concentration of chlorate is constant. So in this particular example, what I'm doing is selecting rows 1 and 3 in order to cancel out not only the concentration of H+, but also the concentration of permanganate, because notice that they're constant in those two rows. The concentration of chlorate, however, changes. So that means that this first fraction and that second fraction are going to be gone. So now you're going to have rate 1 over rate 3 equals concentration of row 3 over concentration of row 1 over concentration of row 3 for chlorate raised to the power of Y. If you carry out those divisions, you're going to find out that this equals 0.325, which is itself equal to 0.3 raised to the power of Y. Taking the logarithm of both sides, bringing the power of Y to the front, so you have Y times log of 0.3, and solving for Y yields log of 0.325 divided by log of 0.3, which is the same thing as 1 if you carry out the calculation. So now we know that the order of permanganate is second order. The order for chlorate is first order. So now we're going to try to find out the value for the protons. And technically speaking, here you can select any rows. And it doesn't really matter which one you select, because at the end of the day, whatever happens to the permanganate fraction and the chlorate fraction, we're going to end up with just a number since we know the value of the exponents. So what I'm doing right here is selecting the first and fourth row because that allows me to change the concentration of H+. It also very nicely keeps the concentration of chlorate the same and the concentration of permanganate the same. So here we can actually cancel out the first terms, but we could have used any two rows at this point. It would have given us an extra step to carry out, maybe an extra two steps. But at this point, when you only have one exponent left to find, you could pick any two rows. It just so happens that rows 1 and 4 makes the problem the most simplistic version that it could possibly be. So now dividing the rate of row 1 by the rate of row 4 and dividing the concentration of H plus in row 1 by the concentration of H plus in row 4 yields the following values, 0.702 and 0.5. So if we take the log of both sides, bring the exponent z to the front of the logarithm, and solve for z, we're going to have log of 0.702 divided by log of 0.5, which yields a value of 0.5. So what this tells us is that the full rate law of this reaction is negative K times concentration of permanganate to the second power times the concentration of chlorate to the first power times the concentration of H plus to the half power. Alright, and like I said before, if you actually want to find out the value of the rate constant, you will have to pick any of these rows, plug in the corresponding concentrations of each of the reactants, raised into the corresponding exponents, and simply divide all of that from the rate of the row that you have chosen, and that will give you the value of K. Alright, so with that example, I think we're in a good position to be able to determine the orders of reactions. So in the next video, I'm going to show you how to calculate the order of the reactions based on a technique called pseudo first order reactions.